Welcome to class meeting 24 of EECE574, the graduate level probability and random process. We have, of course, the most important announcement. Final exam will be taken either during our regular class meeting hours, half on Tuesday, half on Thursday, or if I can find a classroom at this time on Wednesday, we will take that for 3 hours. So if you have any conflict, either with the first option or second option, please let me know as soon as possible. Got it? Handouts, videos are available from our primary webpage, and homework is not yet assigned, but will be assigned soon. And the fourth announcement is related to the topics of voluntary projects. As I repeatedly told you, the topic must be discussed before you take the final exam. Okay, it is not acceptable that after you take the final exam, you want to do a voluntary project. It's not acceptable. The topic must be kind of approved by me, and the format of your deliverable is kind of recorded presentation of you and the PDF or PowerPoint file of that presentation. And it must take more than 15 minutes and probably less than 20 minutes. So around the 15 to 20-minute presentation is required for the voluntary project. You are not required to do the voluntary project because it does not affect your grade, even if you do not submit, okay? But those who submit voluntary project, if I rate that deliverable as kind of acceptable, then your grade will be 1 grade higher than the original grade, okay? I found no correction, clarification, and let's overview where we are and what we are going to do. Even though we just say 9.1 of the populace, but we've covered a lot of topics. And today we are going to almost finish this topic of stochastic convergence, part 1. And we enter into the stochastic convergence related topic today, systems with stochastic inputs. So let me review. We've studied 4 modes of convergence, or 4 different definitions on the convergence of a sequence of random variables. The first one was almost sure convergence, corresponding to the almost everywhere convergence of a sequence of functions. And second one was the convergence in probability or in probability measure that corresponds to the convergence of a sequence of functions in measure. And the third one was the convergence in the Peace mean with p greater than or equal to 1. That corresponds to the convergence of a sequence of functions in the Peace mean. And unlike the convergence of a sequence of functions, we have one more, that is the convergence of a sequence of random variables in distribution. And all these 4 definitions involve the probability measure P. That's the major difference from the convergence of a sequence of functions. And as you remember, for the convergence of a sequence of functions, we first had what? A uniform convergence that does not involve any measure that is a set function. We just handled the uniform convergence and everywhere convergence by using a set on which the sequence of functions converges to a function, right? But for the almost sure convergence, we started to involve the possibly the back, or not necessarily, but anyway, some measure that is a set function. And also in computing the convergence in the Peace mean, we had integration. right? That is also related to the measure, because even though you only know the Riemann integration, there is another integration called the Lebesgue integration that necessarily involves the Lebesgue measure. Okay, Lebesgue integral involves Lebesgue measure. So when we talk about the convergence of a sequence of functions in the Pitts mean, actually we had a measure involved. Similarly, convergence of a sequence of functions in measure, as the name says, it involves the some measure m, right? And different from the sequence of functions convergence, we had convergence in distribution, and that was very interesting. So since our today's topic is related to this convergence in distribution, so let me write down the definition. What was the definition? Given a sequence of functions converges to sequence of random variables converges to a random variable in distribution if the CDF sequence of CDF functions converges to the CDF of the limit random variable on all points of continuity. Okay. So as far as on the points where the CDF of the limit random variable is continuous, you must have the convergence of a sequence of a CDF at that point. Probably I'd better give you an example right away, but we will see that today. Okay? Anyway, this is the convergence in distribution, and there is a simple lemma or a result that shows the equivalent definition. What is it? The sequence of random variables converges in distribution if and only if the sequence of characteristic functions converges to the characteristic function of the limit random variable for all omega. Here, since this characteristic function is nothing but the expectation of e to the j omega xn, which is again defined using the some measure, Lebesgue measure, and so here for all omega is actually in the equivalence class sense. So actually, you may say that for almost every omega, you may say it. Okay. So since there is this subtlety, usually they just say that the characteristic function converges to the characteristic function of the target or limit random variable. Got it? Anyway, we will see the examples today. We also had law of large numbers last time, and we classified the law of large numbers into first, strong law of large numbers, and second, weak law of large numbers. Of course, you can derive or define other kinds of law of large numbers. But here, strong law has the commonality in that they show almost sure convergence. Weak law, on the contrary, shows the convergence in probability. And you know from the result which I didn't prove, almost sure convergence implies convergence in measure or convergence in probability. Actually, if a sequence of random variables if you have a strong law of large numbers, it's automatically a weak law of large numbers. Got it? But the Converse is not true. Here goes some preview. We will see more on the convergence in distribution, especially with emphasis on the central limit theorem. Last time I emphasized that the central limit theorem is often misunderstood. In order to prove the central limit theorem, I recommend you to prove some sequence of random variables converges to what? A standard normal. After you prove that, then scale, okay? Otherwise, sometimes you have increasingly large mean value and you have some trouble. Okay? Anyway, after we study the central limit theorem, we will see some examples, very, very famous. The first one is related to the strong law of large numbers and weak law of large numbers. And as a communication engineer, as most of you are, we do a lot of Monte Carlo simulations. And this is the kind of foundation of the Monte Carlo simulation. Second one is, which I will not prove, but just to introduce, is the Borel-Cantalli lemma, which is often used to show the convergence almost surely. Okay? And the third one and fourth one are related to the binomial random variable. And you've already seen, I believe, in your undergraduate course. First one is the Gaussian approximation to a binomial random variable. And second one is the Poisson approximation to a binomial random variable. Both of them are related to the convergence in distribution. Which means that we are going to derive a sequence of characteristic functions or a sequence of CDFs, and we'll show that the sequence converges to the CDF of a Gaussian or Poisson, or the characteristic function of a Gaussian or Poisson. Got it? And last one is a kind of communication example where the bit error rate of a synchronous CDMA with random sequences. And here actually we will use the central limit theorem. So we are going to use the Gaussian approximation to a binomial random variable. And we will briefly summarize the four modes of the convergences in a single shot. And then we are going to move section 9.5 and 9.1 that deals with the systems with stochastic inputs. The reason why we first study stochastic calculus is because some systems, not every, but some systems, especially continuous time systems, are well modeled by a differential equation of input and outputs. So we are going to see some results from stochastic calculus, and then we are going to move to the systems with stochastic inputs. After that, even though we have just 2 weeks away, we are going to study power spectrum and some other topics, which are also very important. Okay, so here goes the central limit theorem. And let me just start from this page. So suppose this is one of the central limit theorems, as I told you. There are many, many law of large numbers. There are many, many strong law of large numbers. There are many, many weak law of large numbers. Similarly, there are many, many central limit theorems. This is one of the central limit theorem where xi is a IID. And also they have finite mean and they have finite variance. Okay, something's wrong here. Scared. Okay, so first thing you remember is that I can invoke a strong law of large numbers, right? You can do that. In order to, given this setting, probably you remember that if you define a sequence of random variables m sub n, which is defined as x1 plus x2 plus up to xn divided by n, and then if you change n from 1 to infinity, you have a sequence of random variables. And you know from the law of large numbers, this sequence given this condition, converges to what? Converges to a random variable, which is just a constant. Random variable mu sub x, almost sure, and also in probability, right? The first one is from strong law of large numbers, a strong law of large numbers, and second one is from a weak law of large numbers. So here you define the sequence as a sequence of arithmetic mean in Korean 산술 평균. Got it? Then your sequence converges to a constant random variable, almost surely or in probability. Now, what you do is a little bit different. See that? What you do is that you subtract the mean, the common mean in this case, and you divide this centered version by sigma. And you will find that actually that division is not necessary. It's not necessary, but just for our convenience. As I told you, you always had better to prove the central limit theorem using standard Gaussian, which has zero mean and unit variance. The reason why I emphasize in this way is that I want to avoid your making any mistake. Okay? So this division by sigma is not necessary, but just let's do that. Then what happens to this one? What is the mean value of this summand? It's 0, right? What is the variance of this one? Unity, right? So this becomes zero mean unit variance random variable. I didn't say it's Gaussian because there is nothing related to Gaussian yet, right? It could be some strange random variable, but finite mean and finite variance. Be careful. As I told you last time, some random variables does not have a mean value. And some random variables have a mean value, but does not have a finite variance. So this assumption is important, okay, for this theorem. I don't know every central limit theorems, so probably there is some paper on some journal showing the central limit theorem with some other condition. I don't know. Okay? But anyway, this is one of the famous central limit theorem with proof in Peebles, even the Peebles book. But anyway, so you have now a kind of normalized version of x. Then you add up. So this part, the numerator, is similar to this summation, except that you subtracted the mean. Now, here goes the most important difference. Here you divide the sum by n. Here you divide the sum by square root of n. Now what happens? Now what happens? So in order to see the major difference, let's compute the mean of m sub n. What is it in this case? What is the mean ensemble average of random variable m sub n? You take the expectation, then all these terms becomes n times the mean. Now you divide by n. So the mean is mu sub x. What is the variance of m sub n? What you do is that you subtract the mean from m of x. What is that? Mu sub x equals m times mu sub x divided by n, right? So if you subtract this one, you can actually subtract the mean from each xi. So this is same as expectation of what? This one. Now, what is the variance then? Since we assumed the random variables are independent and identically distributed, all the cross terms will disappear, right? Then how many non-cross terms do you have? N, right? Then what is the expectation of x sub I minus mu sub x squared? That is the variance, sigma square. So what is that? N times sigma square divided by n square. Then this is sigma square divided by n. Okay? And now let's consider the limit of the mean. What is that? Mu sub x. What is the limit of variance? It's 0. So the random variable m sub n has mean mu sub x. However, its variance becomes smaller and smaller. And it makes sense because this converges to a constant, right? If the variance is still finite for sufficiently large n, and it does not converge to 0, it does not make sense, right? So division by n makes sense in that sense because variance goes to 0. Variance goes to 0 does not imply strong law, but actually this is used to prove the weak law of large numbers. And probably you will see from the next homework, which I'm going to make probably after today's class meeting. Now, let's see what happens if you subtract, normalize, and divide by square root n. What is the expectation of z sub n? What is the variance of z sub n? What are they? And similar to the mean of m sub n, you can easily check the mean is now 0, right? So mean is 0. What is the variance? Since mean is 0, you don't need to subtract anything from z sub n. You just square z sub n and take the expectation. And again, there are n square minus n cross terms, they all disappear. Here, the same thing, let me correct. There are n square minus n cross terms, they all disappear. And only the squared version of this one, right, remains, and this becomes 1 over n. So here you have n, and you have n times 1, I believe. Is it n times 1? Just a second. Yeah. So you have 1. Always, for all n. So now, since you have scaled with square root n, what happens to the variance? It does not converge to 0, right? The variance is 1. And what we are going to show is this. The limit of z sub n is not just a 0 mean univariance random variable, but it's a 0 mean univariance Gaussian random variable. That is the central idea of the central limit theorem. Got it? So you are given an IID in this case, in this central limit theorem, IID random variables x sub I. What you do is that you subtract the mean and divide by standard deviation, and then you sum up n terms and divide by square root of n. And then this sequence converges to a standard Gaussian. And the proof just shows that the sequence of characteristic functions converges to the characteristic function of the standard Gaussian. Probably you still remember that if some random variable y is a real Gaussian with mean, mu, and variance sigma square, what is the characteristic function of this random variable? That is e to the j omega mu minus sigma square omega square, right? So this is the exponent. Got it? Now, mean is 0, which means that this j times something disappears. Standard deviation is 0. So here you only have negative omega square divided by 2. Got it? So this is a bell-shaped curve in the omega domain. And that is the characteristic function of standard Gaussian. Got it? So let me emphasize, you had better normalize your term when you show the central limit theorem. Now, here goes some quite often misused misuse the central limit theorem. Suppose you just start from this one. What is this one? This is the arithmetic mean, right? Now, what's the limit of this one? As I told you, it converges to the constant. However, you can still claim that for sufficiently large n, it's well approximated by a Gaussian. Why? Let's see this. Here, the central limit theorem says that z sub n is approximately or can be approximated by a Gaussian random variable. Let me say by the standard Gaussian for sufficiently large n, right? That is what we want to use in practical situation, right? The reason why we prove this central limit theorem is to use this result. Zn can be well approximated by the standard Gaussian for sufficiently large n. What does that mean? U says that z sub n is very close to, has very close CDF or PDF with this random variable, right? Now, what was that? Sigma x minus xi minus mu divided by sigma I from 1 to n, and you have square root n, right? So what you do is simple. This is similar to this random variable. Now, what happens if you multiply square root n to z? Then you have what? Sigma 1 over n xi minus mu, right? Now, what happens if you multiply sigma? Sigma zn square root n. That is 1 over n sigma I from 1 to n xi minus mu, right? And the denominator becomes 1. Now let me ask you, how z sub n divided by square root n approximate a Gaussian? It approximates Gaussian with 0 mean and what? Variance 1 over n, right? Because you multiply square root n. What about this one? This one well approximates this Gaussian random. Now you add mu sub n, sorry, mu, then what happens? You have xn, which is m sub n, and this is well approximated by this one. Got it? So it seems that your central limit theorem claims, again, what? This one. Arithmetic mean can be well approximated by a Gaussian random variable with mean mu sub x and standard, sorry, variance sigma squared divided by n, right? However, in the proof, you don't do this. Okay? In the proof, you don't show this converges to that one. Okay? What you prove is that z sub n converges to the standard Gaussian, or this one converges, sorry, let me see. Not that one. Or what you do is that you show this term is well converges to a Gaussian with a 0 mean and variance sigma squared. since you multiplied sigma. Okay? But anyway, proving this converges in distribution to that random variable is same as this one. That's why I recommend you to always just normalize or standardize your term to prove the central limit theorem. Okay. So this is one very general central limit theorem, and here goes a very special one. So here goes another central limit theorem. Actually, this is just an example of that theorem. But this theorem is rather complicated to prove, but this theorem is much easier to prove. That's why I love this example. So let's see. Here you have x sub I, that is IID random variable with value -1 and +1 with equal probability. So it's either -1 or +1 with probability half and half. Got it? Now, you sum all of them and divide by square root of n, not n. So this is not the arithmetic mean. This is arithmetic mean times square root of n. Got it? And what happens to this one? And you don't need to prove actually. What you can do is that you just compute the mean and you just compute the variance. What is the variance? Variance is 1, right? And from this, IIDness and finite mean and variance, you can just invoke the previous central limit theorem. And what's the result? You sum up the standardized version and divide by n, and it converges to some standard Gaussian. Right? But here 1 is 1, 0 is 0. So what do you have? This converges in distribution to a standard Gaussian. Got it? And we are going to prove that. So there are two ways to prove that. The first one is to find the CDF sequence, and the other is to find the characteristic function sequence. Usually, we find the characteristic function sequence. So let's compute the characteristic function of this random variable x. What is the characteristic function? That is defined by the expectation of e to the j omega xi. And whenever you have expectation, remember this, expectation is value times probability summed up, right? So you consider the value of xi, 1 or -1. If xi is 1, then you have e to the j omega times 1 with probability 1/2, and you have e to the j omega, -1 with probability 1. Then what is this? This is simply cosine omega, right? From what? Euler's identity, right? So let me see. Yeah. Now, then what is the characteristic function of this sum? So let's say this as y sub, let me see, is it y sub I? It's g sub n, right? Okay, we defined it as z sub n. Now, what is the characteristic function of z sub n? That is e to the j omega square root of n sigma xi, right? Then what is this? Summation can be written as a product. So you have square root x1 e to the j omega x2 divided by n dot 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 e to the j omega xn divided by root n. And from the independence, this becomes the this becomes the product of expectations, right? And you have characteristic function of x sub 1 and evaluated at square root of n dividing omega times up to x sub n of omega divided by square root of n. Got it? Now you plug in this result to that one, and eventually you have what? Cosine omega divided by square root of n raised to the power of n. Got it? So your z sub n has this characteristic function, right? Now, what do? We take the limit of that sequence of characteristic functions. And we compute the limit of cosine omega divided by square root n raised to the power of n. How can you compute the limit of that function? How? How can we find that? Actually, this consists of uncountably infinite number of limit of sequence of real numbers, right? If you fix omega, you have a number sequence, right? And when you have a sequence of numbers, what do you have? Suppose you want to compute the limit of a sequence of numbers x sub n. And if you have a monotonically increasing function, strictly increasing function, then what do you have? F monotone increasing. Monotone increasing. Or just monotone decreasing, it doesn't matter, but anyway, F monotone increasing. What happens? Or let me see. I'd better say continuous. Okay? That is better. Continuous function. Then what happens? What is the limit of f of x sub n? If f is continuous, a continuous function. Continuity of a function allows the exchange of limit and your function operation. So continuity means that this is same as f of limit of xn. Got it? So this is one of the most important results from the introductory real analysis. Got it? Continuity means you can put this limit inside the argument. Okay? So instead of finding this one, what you do is that you find the limit of log of that one. So here, you take the log of the characteristic function and derive the limit, and then you take that one as the exponent of exponential function, because exponential function and the logarithmic functions are inverse functions. Okay, so here goes the trick. So instead of directly considering the limit of this function, you derive the limit of log of the characteristic function. And then after you got the result, you will put that result in the exponent of the exponential function. And let's see what happens. What is the limit of this one? And still formidable? What is this? And actually, you can expand the cosine function using the Maclaurin series or Taylor series. Okay? And then what you can do is that you use what? The famous result. Or the famous result. Something like that. Okay. And actually, some people define the number e as the limit of this or that one, right? So you use that one, and you can show this converges to that one. Or you can directly apply L'Hopital's theorem to show this one. Okay? And probably you'd better apply L'Hopital's theorem. Then it converges to negative omega square over 2. So what you can say, the limit of the characteristic function is simply e to the this one. What does that mean? It's the characteristic function of the standard Gaussian. So our proof is done. We've shown that the sequence of characteristic functions of z sub n in this problem converges to the characteristic function of the standard Gaussian. Got it? Now let's see some implication of this one. What does this mean? What does this mean? And some of you probably wondered, what does this mean when you first saw this example in your undergraduate program? So here goes some in-depth approach. So let's see what is the CDF of z sub n as a function of, say, z. Okay, what's the shape of that one? And you remember z sub n in this case is simply the square root n x1, x2 up to xn. What is this one? 1 or negative 1. What is this one? 1 or negative 1. What is this one? 1 or negative 1. So it ranges, if you just plot a histogram, it ranges to what? Square root n to negative square root n. If xi's are all ones, then you have n times 1 divided by square root n, right? So the maximum of z sub n is square root n, and the minimum is negative square root n. And what about other values? And you know that actually you have two steps. If you just consider square root n times z sub n, what do you have? You have from negative n to n, and the next one is negative n plus 2, dot, 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 and you have n minus 2, then n, right? Because you can't have n minus 1, because it is either 1 or negative 1. If 1 defects to negative 1, you have to subtract 2, right? Not just 1. So something like that. And what is the kind of mass located at each point? And you already studied when you are a high school student. What is that? Here you have the mass is 1/2 raised to the power of n, right? Because every xi must be 1, and that is, what's the probability? Half times, half times, half. So you have here again, probability mass is 1/2 raised to the power of n. What about others? And now here kicks in the binomial coefficient, right? And you know that they have higher and higher probability masses following, and you may say that, okay, it follows the Pascal's triangle or something like that. Something like that, right? Is it? Yeah, I believe so. So here, this one is 1/2, and you have n choose 1, so you have n, and here you have 1/2 raised to the power n, and n choose 2, something like that, right? So this is what? This is the probability mass function. What about the probability mass function of z? Same, you just scale by square root n. So you have 1/2 raised to n, and here you have negative n plus 2 divided by square root n, here n minus 2 divided by square root n, and same mass, right? This is the probability mass function of z sub n. And obviously, z sub n is a discrete random variable. So what about its CDF? Sorry. Here is the origin. What is your CDF? CDF must look like this. Here you have a jump, right? And what is the height? 1/2 raised to power of n, right? And here you have another jump, something like that. And it's monotone increasing, and eventually here at square root n, you reaches 1. Okay? So your CDF of Z sub n is what? Piecewise constant. And that is obvious because it's a discrete random variable, and you know that the cumulative distribution function of a discrete random variable is what? Piecewise constant. And what happens if you increase n? This tends to negative infinity. This tends to positive infinity. And how many points do you have? N minus 1, right? So your length becomes sublinearly increased because the length is square root n. Now your points increase linearly. So it's like you increase sublinearly, but the points increases linearly. However, any sufficiently large n, still the CDF is what? Still piecewise constant. It has jump discontinuity. But the central limit theorem claims what? The limiting CDF is a smooth curve because it's the smooth curve of the Gaussian CDF, right? What they claim is that something like this. How can a piecewise linear function can be a smooth function? Strange, right? But at each point of z, we can show that this sequence of function converges to this point. Got it? It's very similar to the mean pass over some discrete random process. You remember. Suppose you have either -1 or +1 during some period t, BPSK signal with rectangular pulse. What is the sample path? 0. That is a continuous function. However, the mean path, every sample path is discrete, right? It's discontinuous. Similarly, even though every CDF of Z sub n for finite n is a piecewise constant function, its limit function can be a continuous function. So it's somewhat strange, right? And what's the use of this one then? Here, let's remind our definition of the CDF. CDF is simply the random variable less than or equal to this argument value, right? So the convergence in distribution is in the core of the central limit theorem. And what do we say? We can just simply use the Q function. If we have proved the central limit theorem, right? See that Q function is often tabulated, for example, in MATLAB and other functions, or even though it is not tabulated, there are many functions available so that you can just grab it from the web and use for Python programming or C programming and something, okay? So whenever you want to compute some probability for sufficiently large something, it's the best. The convergence in distribution is enough. You don't need to prove almost sure convergence. But sometimes almost sure convergence is very easy for some specific example. In that case, prove almost sure convergence. Then what happens? Almost sure convergence implies convergence in distribution, right? So having this in mind, let's go to the last example. No. Let's not do that. Let's just follow the order. So, okay, let's see the, we've just seen the Gaussian approximation to binomial. Okay. And you may say, that, what binomial? So let me do this. Suppose you have x sub I now is really binomial. So it's either 0 or 1 with probability half. Or if you don't like this, then let's have this. Xi equals 1 with probability p, and xi equals 0 with probability 1 minus p. Okay. Now, xi is a IID. And you want add up that xi's. Sorry, this is not SM sum. Sum is just x1 plus xn. Now, what is the name of the random variable s sub n? That is a binomial random variable with parameter n and p. So we usually say that Sn follows the distribution b and p. Am I right? Right? And as you learned in high school math, actually, when I was a high school student, we just memorized the result. What is the mean of S sub n? NP. What is the variance of S sub n? NP 1 minus p, or NPQ if you want to define 1 minus p as q, right? And the the Gaussian approximation to binomial means that this random variable S sub n is very close to the Gaussian random variable with mean something and variance something. What would be that Gaussian random variable? Of course, mean NP and variance this one. So you want to say that this converges, or this is approximately equal to, in some sense, with some random variable S that is Gaussian with mean NP and variance NP, 1 minus p. How can you prove this one? Do you just start from S characteristic function of S sub n and show the convergence of the characteristic function to the characteristic function of this one? What do you think? As I told you, this is central limit theorem, not just the convergence in distribution. So what I suggest is that you make each one as what? Mean zero, unit variance random variable. So what I suggest is that you subtract the mean from Sn. So you subtract NP, right? And what do? You divide by NP, 1 minus p. That is the standard deviation. Then this random variable has what? Zero mean and unit variance. Now, you can show that the characteristic function of this one, so characteristic function of this one converges to the characteristic function of zero mean unit variance Gaussian. And then what do? As I told you, you just scale that one by multiplying square root n times p times 1 minus p. Then your variance goes back to n times p times 1 minus p. And then you add up np. Then your mean goes back to np. Okay? So you can prove that without any difficulty. Okay? Actually, after, for example, you substitute p with 1 over 2, you go back to the previous example. Actually, the same thing. Now, what about this one? Poisson approximation to binomial. Actually, we do almost the same thing. But when we take the limit, we do some trick. And I believe, okay, it seems I didn't write here. Let me find. I put somewhere the proof of that. Just a sec. Okay, it seems it's not here. And probably here. Okay, it seems I didn't write it. Okay, so yeah, let's just derive it. Okay. So here, let's calculate the characteristic function of xi, which is e to the j omega xi and e to the j omega with probability p and e to the negative j omega with probability 1 minus p. And what about the sum? So what is the characteristic function of Sn? This one raised to the power of n because they are IID random variables. But before you do that, let's do some trick. I remember is that we group like this. Am I right? I'm not sure. Plus e to the negative j omega. Am I right? Yeah, I believe so. Yeah, I'm not sure. I'm losing confidence here. Okay. Anyway, so what you do is that you raise this one to the power of n, and then you take the limit. But you just not let n tends to infinity. If I remember correctly, what you do is that you let n times p fixed and take n tends to infinity. So which means that actually your p is not fixed. Your p reduces. Why we do that? Because this Poisson approximation to binomial is applicable when p is very small. Okay, when p is very small. What does that mean? Mostly 0 appears, right? And in some case, you have a few ones from x1, x2, x3. Right? In order to have that one, you keep as, yeah, np fixed, and then you let n tends to infinity. Then you can show that this characteristic function converges to the characteristic function of a Poisson random variable. Okay, I will put it in the homework so that you can feel the proof of the Poisson approximation to binomial. By the way, you can easily find the proof of these two from the web. So the homework may not be that difficult. But anyway, what is important is that for the Gaussian approximation to binomial and for the Poisson approximation to binomial, what you do is that you show convergence in distribution. But the difference is that since this is the central limit theorem, you normalize, again, as I told you, you normalize and then show the convergence to the convergence of a sequence of characteristic functions to e to the negative omega squared divided by 2. But here, what you do is that since it is not a central limit theorem, you just take the limit of the characteristic function of Sn. But if you just fix p, it blows up. So here, you fix n times p and let n tends to infinity. And you may say that, what's that then? But it makes sense because anyway, what we are going to do is that for sufficiently large n, what would be the characteristic function of that summation? And now let's consider just the sum of this one. If p is very, very small, probability of Sn equals 0 will be very large, right? Probability of Sn equals 1 will be some value. 2 will be another value. 3 will be some other value. But Sn takes the value 0, 1, 2, something, up to actually n, right? So you may wonder, wait a minute, Poisson random variable can take any non-negative integer. You're right. So in some sense, they can never be the same, but their CDF or their characteristic function is very close for sufficiently larger. So this is the core of the Poisson approximation to a binomial random variable. Okay, what else do we have? Okay, so we've done this one and that one. Okay, then let's see the bit error rate of a synchronous direct sequence spread spectrum multiple access. And for that, I will write it. Okay. Yeah, write it here. For direct sequence spread spectrum multiple access with random sequences. So this is probably the first communications example. And this model is very simple. It's a vector signal model. So here is your received vector. And for simplicity, let me assume you have real valued vector observation of length n. So y equals y is your observation. Here, y is a real length n vector for some n large. And here you have sigma I from 1 to usually k, b, I, sorry, let me use k, lowercase k, and some s, k plus n. And here, sk is a random vector actually, where sk is either -1 or +1 with vector length n. So this one is, for example, something like this. Okay, so that vector sk is consisting of 1 and -1. And here, n is Gaussian. Real Gaussian with, let me see, variance, just sigma square. Yeah. So, sorry, let me be k. There are k bits, and you may say that each bit from each different user. Okay, so here is your base station, for example, and the first user, second user, kth user, transmitting a signal that is sampled and collected as a vector of length n. And this is mathematically modeled, for example, as this equation. This first user use random sequence S1 times its bit B1 and B2 times S2 and BK times SK. And then they are summed and corrupted by the Gaussian noise. And got it? And one of the simplest receiver to extract the information about B sub K is this one. What you do is that you transpose B sub K to Y, assuming that the receiver actually has the same random number generator for that one, that one, that one. So the receiver knows the spreading vector, not the symbol. Got it? So the receiver actually implements a matched filter. Assuming there is no interference, only Gaussian noise. Then this is the matched filter. And what is this output? So you multiply that one and find that bk times n plus sigma k not, let me see, k prime, and you have bk sk prime, k primes, transpose sk plus sk transpose k prime n. Okay. What is this one, by the way? You have IID Gaussian random variable multiplied by 1 or minus 1. Since mean is 0, actually this is again a Gaussian random variable. Okay? So this is Gaussian. What is the mean and what is the variance? Mean is 0. The variance is what? Variance of this one. And you can show that is n times sigma squared. Okay? So if there is no noise, your signal is bk prime times n. So if you plot, then this is 0, and your desired signal is either n or negative n, and this one is Gaussian, so you have some density like this. So if there is no interference, what is the probability of bit error? Probability of bit error, bk not equal to bk hat, is probability of bk prime not equal to sine of sk prime transpose y equals probability of what? Your received signal is less than 0 when bk prime is 1 times probability of bk prime is 1 plus sk prime transpose y greater than 0, bk prime is negative 1, probability of bk prime negative. And if we assume bk's are equally likely, then this is 1/2, this is 1/2, this probability same as that one, and what? This is simply Q of the standard deviation, right? And you have the mean value n times 1. Just for simplicity, for convenience, let's put our power. Okay, so let's say that the P. Then what do we have? We have here square root of P, and P here, right? Oh, sorry. Let me see. Yeah, square root of P. Got it? So this becomes Q of P over sigma squared, as you know from the matched filter theory. Got it? But you have now the interference. Okay? So without multiple access interference. Now with multiple access interference. What do we have? We have this term, right? And unfortunately, this term is no Gaussian random variable. What do? We invoke the central limit theorem. So what we do is that we properly normalize this term and show that this term converges, after normalization, it converges to a Gaussian random variable. And then we scale and scale, go back to that one, and invoke Gaussian approximation. So what we do is that we compute the mean and variance of this one. Mean is, of course, 0. What is the variance, by the way? What would be the variance? So here they are K and K prime are different. So you have either 1 or -1 here in K prime vector, Sk prime, and you have either 1 or -1. If you multiply, it becomes either 1 or -1. Okay? And you have K, capital K, 1 or -1. And what is the variance of that one? We've already seen it, right? We already have seen when xi's are either 1 or -1, and you sum up n of that, what happens? Its variance is n. In this case, this one has 0 mean and variance n. That is the length of the vector sk. Now, you have how many of them? Capital K minus 1. So your variance becomes this one. And now you have P. So your variance of entire one becomes that one. And this will become the variance of your approximated Gaussian interference. So now you have is what? Probability of bit error approximately equal to Q of, here goes your desired part, and here is your variance, that is n sigma square plus what? This one. And let's put everything inside the square root, and you have Pn square, and you have n sigma square plus Pk minus 1. Now n disappears. Let me see, something's not quite correct. Just a second. Yeah, I believe. Just a second. Something's not quite right. Just a second. Okay. Yeah. It seems I miscomputed the variance. And sigma square. Just a second. Just a second. I believe I'm correct. Yeah. So you have square root of Pn divided by sigma square plus Pk minus 1, something like that. So as you see, if you don't have an interference, you have this. Sorry, you must have n square. Yeah. Sorry, np time np divided by sigma square. Now you have this term in the denominator. So your performance degrades. Now you may wonder, how accurate is this approximation? And you will be amazed if you plot the simulation result by using this Gaussian approximation when K is large enough. It's very, very close, up to tens of dB in the signal to noise ratio, something like that. So here, what is concerned is to compute the probability of bit error. And probability of bit error usually involves probability of some random variable greater than, less than, something like that. And these probabilities are all related with what? The CDF, right? So as far as CDF converges to something, we are happy when we want to say this approximation is accurate enough for sufficiently large n. Then what kind of convergence do we need in distribution? And one happy thing is that every other 3 definitions of convergence, almost sure, in probability, in the PISME, they all imply convergence in distribution. So when you compute the probability, and if you want to make an approximation, actually proving convergence in distribution is enough in most of the times. However, sometimes proving using mean square convergence is much easier. Then prove that. No problem, because that implies the convergence in distribution. Okay? But usually directly proving the convergence in distribution is much easier. So whenever you see some asymptotic result, usually they prove convergence in distribution and claim that here is our error probability, and this is our simulation result, and this is our Gaussian approximation or our sum approximation. They are almost the same. Why that is justified? Because they prove the convergence in distribution. Okay, it seems that I couldn't fully cover what I originally planned in the beginning of today's meeting. So next time I will cover these two topics and summarize and move to the stochastic calculus. Okay, that's all for the day.